Center of mass is a new topic that we didn't have in the particle model, but that we do need to work with in the rigid body model. The idea is that we create a special position, which is defined to be the center of mass, and in 2 dimensions we would define its position in x and y. We can calculate it by summing up every single piece of mass and its position in that direction. Then you divide out the total mass. And so this is the right way to think about it for a discrete system, such as this object, where each of these particles has a mass. Maybe they're all the same mass, maybe they're not. You would then add up the x position of every single piece multiplied by the mass of that piece, and you would find the average. You would then do the same thing for y. So the notation here is just a simple way to write it, but all we're saying is that you add up every single piece of mass, multiply by the position it's at, and then divide by just the sum of every single piece of mass. So the top equation and the bottom equation are completely identical, just slightly different ways of writing it. So this is really helpful, again, if you have a discrete array of masses, but it's going to be less helpful when the mass is distributed in a continuous way. So we're going to come back to that in a second, but first let's try to figure out why we actually care about this. So when we had translational motion, we were usually talking about motion of a particle, and you can think about the particle being equivalent to its own center of mass. When we have combinational motion, such as this triangle, if you imagine tossing this through the air, translation, our old-fashioned motion, is going to be the motion of the center of mass. Rotation, on its own, is going to be rotation around the center of mass. Now, in not every situation does an object rotate around its center of mass, but it's freely moving in space because you, for instance, have thrown it somewhere. It does naturally rotate around the center of mass. So it can have rotation around other axes, and we will look at that, but think of center of mass as kind of the default place that it rotates around. So we need to think about this because if we want to calculate translational motion of a more complicated object, we need to know where the center of mass is, and anytime we do rotation, it's really relevant. So let's do another example with a discrete system before moving on to the more challenging situation. So in the discrete system in this case, we have basically 2 pieces of a barbell. They have different masses, and we want to find where the center of mass is. Now, in this case, we know that the center of mass in y is just going to be really this straight line in dividing it in half. I can place the 0 of my y-coordinate system wherever I want, and if I place that right along the bar, then it's simple. The other thing about this is we're treating the bar itself as having a mass of 0. That's not always going to be the case, but for right now it will be. So you need to define your coordinate system. We need to define we're calculating the center of mass in x, and so you must define where x equals 0. And you have to keep that consistent. You can't say that x equals 0 here, and in the center of bar, and here. You have one place where x is equal to 0. And you do one direction at a time. We're going to do x. So we see that this mass is at 0, this mass is at 0.5 meters because the bar is half a meter long. What you then do is go back to this equation. We only have 2 pieces of mass to worry about. So on the top, you take the position, and in this case, we're actually approximating each of these balls as basically a particle itself. And that's okay, or at least in this case, we're putting the center there. So we're saying the center of the first ball, which is at 0, I've defined it that way, and then the center of the second ball is at 0.5 with their masses. You then add this up and divide by the total mass, and you get that the center of mass is 0.1. Note that this is going to be a positive number. Your 0 is here, your positive x direction is to the right, and so that tells you where the center of mass is. Now note that you could have picked a different place to be x equals 0, and you would have gotten physically the same point, but it wouldn't have the same number based on how you defined your coordinate system. So that's why it's incredibly important to define your coordinate system, because a given distance that the center of mass is from the ball on the left will always be the same. But if you just say, hey, my center of mass is at, say, 0.05 meters, well, that's true if you picked this point to be y equals 0, but it's not true if you picked any other point. So make sure you define your center of mass. I'd like to discuss a practice problem that is in the book that I think is a really good example of what's going on with center of mass, because it's a little counterintuitive. We have a bat, and we know where the center of mass of the bat is. And one way to think about that, though we'll talk about this in a later section, is you could actually balance the bat here. So you could put your finger here, or you could put a little fulcrum there, but the bat actually would balance above that point. So we know where the center of mass is, we can find it. We then cut the bat there. Which end is heavier? Now, one option is the left end, one option is the right end, one option is that the masses are the same. I think that it's an easy mistake to make to say, well, the masses are the same because it balanced there, so that must be what's going on. But that's not actually the definition of center of mass. Remember that center of mass isn't just where do you have equal mass on each side. It depends on the position. Now you might say for this, well, where do I actually define my position? And what you can do is for each of these pieces, actually define the center of mass for that one piece. Now for the right end, that's easy since it's pretty uniform. The left end is a little bit harder, but I think the center of mass might be somewhere like there. So, what do we see now? The center of mass, if I choose my coordinate system, I can actually pick 0 to be in the middle. I've picked x equals 0 to be in the center, and I then can write out what my center of mass must equal. The term on the top must be equal to 0, since the term on the bottom can't possibly be equal to 0. So that means that the negative term on the left must equal the positive term on the right. And notice that this distance, the distance on the left, is bigger than the distance on the right. So once you have these two pieces of information, the only way that this can be true is if the mass on the left side is smaller than the mass on the right side. So the mathematical argument might not make a lot of sense to you, and that's okay, but I'm trying to give an example here. The basic idea is that you can't say that the masses here are equal because that isn't the definition of center of mass. The definition of center of mass depends on where the mass is located. So because this right piece of the bat on average is closer to the fulcrum point, that means that it must have a bigger mass to cancel out the fact that this left piece on average is further from the fulcrum point. And so therefore the closer mass must be larger than the farther mass. So again, a little bit of math to show that. The main point I wanted to make here was that center of mass is not just about balancing the quantity of mass on each side, but the distance averaged quantity of mass. Or another way of looking at this is that it's the mass average position.